So till now, this is our neural network that was based upon radial basis function. This was your input layer. This is your radial basis function layer, and corresponding to this, we just try to find out their receptors. And the overall process followed for finding receptor was that we represented the all your input space using these dots, and after representing them in space, we clustered them using our nearest neighbor method, and after finding individual clusters, we found their centroid denoted by mu1, denoted by mu2, denoted by mu3, and denoted by mu1. Why m? Because there were m number of radial bases, and the piece dimensional space was to be extended to your m dimensional space. Now let us get into more details. What is happening is that the overall input space is now divided into m number of clusters. Now each of these clusters can be seen in the form of a Gaussian distribution, and this Gaussian distribution is having mean as equal to mu1. So this mu1 or you can say the mean of your Gaussian distribution is equal to the centroid of your clusters being formed using nearest neighborhood method. So this mu1 is going to act as your T1 used here. This mu2 will going to act as your T2. This mu3 will be acting as T3, and so on. This will act as your T of m. So each individual portion, each individual space, each individual cluster is expected to follow your Gaussian distribution. And for this Gaussian distribution, this mu1, which is now named as T1 in case of receptor, and this individual distribution is having sigma as your standard deviation. And as we know that square of sigma generates our variance. So your Gaussian distribution function makes use of your mean of a particular cluster, that is given name as your receptor now, and this is your variance, actually sigma 1 square variance for cluster number 1 being represented as your Gaussian function. On the same lines, for cluster number 2, its mean was equal to mu2, that has now become equal to receptor for this cluster, and its variance that is found by just squaring your standard deviation is given by sigma of 2. So in this way, these all terms, these all Gaussian functions are to be evaluated. Now look at some more details about Gaussian distribution. The Gaussian distribution, as we all know, follow this behavior. Here this represent mu, or you can say the mean of your Gaussian distribution. The standard deviation by unit place, or you can say mu plus sigma, when sigma equal to 1, covers almost this area. When sigma is equal to 1, it covers 0.68% of your total area, and this area keep on increasing if we move at in this direction here and in this direction here. At sigma mu plus sigma equal to 2, it covers more area. So in this way, this is the significance of your standard deviation, or you can say variance, in case of your Gaussian distribution function. Now move ahead. Now we have to calculate this sigma square, this variance, or it further is coming from the calculation of your standard deviation. For calculating this sigma, we have to consider a space that is a representation of your receptors, or you can say your mean values of clusters. So this is the space representing your receptors, and as we know, there were m number of receptors or m number of radial basis function, so it will contain your m number of receptors. For finding the standard deviation around your first radial basis function, we have to follow this equation. We will say that it will be the average of the summation of T1 minus the negation for all other clusters, means T1 minus T2 plus T1 minus T3 plus T1 minus T4 up to T1 minus Tm. We'll square them all and add them, and after adding we'll just divide them by the number of total clusters, total receptors present, and then we'll take a square root of this. This will result in your calculation of standard deviation around your first cluster or around your first receptor unit, or in turn you may also say that around the centroid of your first Gaussian function. It will calculate your sigma of 1. Now it can be easily generalized for ith cluster by putting just I here and just by replacing this one again with your I. So we need to calculate this. So if we replace this 1 by I and this 1 again by I, then we can just generalize it, and we'll be calculating sigma of I, where I varies from 1 to m. So in this way we are going to calculate m number of standard deviations, and further which will further lead to the calculation of variance, that is sigma of 1 square, sigma of 2 square up to sigma of m square, which are to be used at this layer to produce the output. Means at this stage we know that x is our input pattern given to it, T1 is the receptor, or you can say mean of your Gaussian function for individual cluster, and sigma we have just calculated here. Now we'll make use of these all known terms to calculate output at this your radial basis function layer.